Hi, I'm Antonio Sala. In this video, we are going to discuss how to obtain the statistical description, mean, variance, covariance with several things, of the partial derivatives, the gradient, let's say, of a stochastic process. We discussed the generic non-stationary case in another video. We'll briefly review it here, and we'll concentrate here in the stationary case. In the case, covariance is only dependent on the difference or on the distance between input points. The overall motivation of studying the derivative stuff is that we may have, let's say, position and speed measurements of something which is moving randomly, and integrating position and speed measurements may help me obtaining better position estimates, or why not, better speed estimates. The formulas we derived in another videos for a generic non-stationary case will readily apply to the stationary case, as we will immediately discuss below. Let us review the general case. We have a stochastic process, which actually may be understood in lay terms as a random function. For each value of x, f of x is a random variable with mean bar f of x, which we will assume is known, and there is some statistical correlation between the values of f at a point x and the values at a point x prime. Prime does not mean derivatives here, okay? It's just a different point. That statistical correlation between the values of f at different places will be encoded by a covariance function k with two arguments, x and x prime. This covariance allows us to estimate the value at x prime given observations of the value at x. That's the standard Kriging or kernel regression developed elsewhere. Under some technical conditions, f may be differentiable. We are not discussing those technical conditions, just imagining that, okay, if we have a mass subject to random forces, then the derivative of its position exists, means something, is the speed, and even if mathematically defining all that can be sort of tricky, well, okay, as engineers, we do understand what the speed of a randomly moving pedestrian, let's say, is, okay? If we think on what the mean of the derivative is, then we can prove that the expected value of the derivative is just the derivative of the expected value. So if this is the position of something, then the derivative of this will be the expected value of its speed. It's kind of common sense. In other video, we proved that if we know the covariance k between 2 points, then these two formulae hold. The covariance between the value of position f, let's say, at a point x and the slope, it's the partial derivative of the covariance with respect to the kth component of its second argument. The formula below, it's actually the same, interchanging x and x dot, because, covariance must be symmetric. So basically, the covariance of something with respect to its gradient, it's the gradient of the covariance function, informally speaking. And we also have this expression regarding the covariance of the ith partial derivative at point x and the jth partial derivative at the point x prime. In that case, it's the cross derivative. And informally speaking again, we say that the covariance of the speeds, the covariance of the partial derivatives, is the Hessian of the covariance. So, we are now in condition to particularize that to a stationary process. Stationary process has this property. The covariance k, it's actually a function that depends only on the difference between x and x prime. So it's another function kappa of h, given h, the difference between x and x prime. And of course, as covariances must be symmetric, kx prime must be equal to kx prime x. So if I replace h by minus h, kappa must give me the same value, so it must be an even function. If x is one-dimensional, then kappa must have this symmetry. Otherwise, it would be meaningless in a statistical sense. Good, so this is a stationary process. Everything I explained up to now is basically a summary of previous content. The only thing we need is replacing in these expressions k by this kappa here and see what we get. So let's do it. If we see this, the covariance of f at x and f at x prime kth derivative, well, we replace x prime by x plus h, and so this is what we had above, the partial derivative with respect to the kth component of the second argument, but okay, that's the same as the partial derivative with respect to the kth component of h in this expression, because h is only in the second argument, and as that function is actually kappa of the difference, which is h, then we have the expression I wanted to obtain, which is that in a stationary case, the covariance between position at x and speed, let's say at x prime, h units away, it's the gradient, the suitable derivative for a difference h. If this is kappa, the symmetric function, then the derivative of kappa will be something positive here, 0 at the origin, negative there. Well, okay, then evaluating that at h is what this expression says we must do to obtain the covariance between a process and its derivative. Okay, if it's more multivariable, the derivative with respect to the kth input, it's the derivative of kappa with respect to its kth coordinate of the increment h. We may wish to obtain the covariance between the derivative of x and the function at x prime. X prime is x plus h. First, we should see that due to symmetry, it's kind of swapping x and x prime up there. Then h will change sign if we swap x and x prime. So it's should be kind of evaluating this at minus h. And in fact, that's what we do. We keep x prime, we say that this is x prime minus h. We apply the formula, in this case the derivative with respect to the first argument as we put here, but it's essentially the same as above. This is kappa of minus h, so the derivative with respect to the kth coordinate of this first argument is just minus the partial derivative of kappa, which in fact is the same as evaluating the thing above at minus h, because if this is kappa, then the derivative at a point h is just by symmetry the derivative at minus h changing sign. So basically those two lines are exactly the same formula. You can evaluate the gradient at minus h or evaluate the gradient at h and change sign, and it's just the same because of the symmetry of the covariances. Good, so we have the expression for the covariance between position and velocity, let's say. So we end up with this to use in later numerical examples. And let us now discuss the covariance between derivatives with respect to different coordinates, if multivariable, and the different points. Well, the basic fact is that we will use the formula we derived elsewhere and which we just wrote a few lines above, but replacing x prime by x plus h. So this thing, k of x prime, will be little k kappa of the difference. This is h. So this Hessian-like formula, the derivative with respect to the first argument xi will be, by chain rule, we'll need we'll need to multiply by -1 because we are subtracting here. So we get this minus arising from this derivative. As this difference is h, we need to take the derivative with respect to the ith coordinate of h and change sign, and then the derivative with respect to the jth coordinate, x prime here, jth coordinate of h here. Well, we will no need any further sign changes. So this is the important formula that we will use later on in numerical examples, which says that the covariance between the partial derivatives of a stationary process, it's the Hessian, the cross derivative, with its sign changed. In this formula, ending here, we were using partial derivatives with the k or ith, jth coordinates, whatever. But in the particular case, when the stochastic process depends on a single dimensional variable, in this case, this is a particular case in time series. So in those kind of problems, the input variable, we call it time, lowercase t. Well, in a single dimensional time series, we just have one thing to take derivatives of. So we don't have h, I, h, j, we have just h, no partial derivatives, converted to just ordinary derivatives, d. So in this case, we will have just the derivative of kappa, and in this case, we will have the second derivative of kappa. So these are the final formulas for a time series. The covariance between position and speed, if we interpret it, as a randomly moving thing, well, the covariance between position and speed at two different times is the derivative of kappa at h. And the covariance between speed at two different instants, so speed is a stochastic process, so this will be the second derivative of kappa with changed sign, will tell me the covariance function of the speed considered as a standalone stochastic process. So good, we've finished with this. Let's summarize. In this video, we applied the generic theory over the partial derivatives of a stochastic process to the stationary case. So we get functions that depending only on the difference between the points we were trying to evaluate things. The covariance between a process and a partial derivative of it is the partial derivative of the kappa function. The covariance between partial derivatives at points separated h was the suitable cross second derivative evaluated at h and changing sign. And when we are speaking about single dimensional stochastic process, about time series, so we have, let's say, position and speed, then covariance between position and speed, it's the derivative of kappa. And the auto covariance of the speed itself, it's the second derivative of kappa, changed sign. This is it. Thanks for watching, and subscribe to keep updated on new content. Bye!